Welcome to EDUCARE. In this video, I'll explain the turns ratio, voltage ratio, and current ratio of transformer. Generally, we become confused about the current ratio. Then, what is exact current ratio and what is approximate current ratio will be explained very clearly in this video, and we also discuss about the Phasor diagram of transformer. Okay. This is a transformer and the core of the transformer is drawn separately. Whenever an AC voltage is applied to the transformer, then a no load current I0 will be drawn from the supply. The I0 has two components, IW plus I of mu. Okay. The IW is represents the iron loss of the core of transformer and I mu is responsible for production of required flux. About no load current, equivalent circuit of transformer in part 1 class, it has been discussed very clearly. If you have any doubts, please go through that video. Link will be given into the description box. Means due to magnetizing current I mu, a flux will be produced into the transformer core. This is the flux phi. The flux passes through the transformer core like this. This is the flux phi, and these flux link both primary as well as secondary winding. This flux is called the working flux or mutual flux. Again, regarding working flux and mutual flux, equivalence in equivalent circuit of transformer part 3 class has been discussed very clearly. If you have any doubts, please go through that video. Link will be given in the description box also. Since the voltage is AC, therefore the magnetizing current will also be AC. That means sinusoidal. This is the magnetizing current versus omega t. It will be a sinusoidal current. Again, the flux phi will also be an AC, alternating. Since the flux is alternating, according to Faraday's law of electromagnetic induction, E proportional to d phi dt. The primary winding feels that the flux inside the winding changes with time, then an EMF E1 will be induced into the primary winding. Okay. Similarly, this flux also link the secondary winding, and this secondary winding also feel that there is a change of flux and EMF will be E2 will be induced into the secondary winding. Let the primary winding has N1 number of turns and secondary winding has N2 number of turns. Now, whenever a load is connected across the output terminal of transformer, this is the load. Since there is an induced EMF E2, as soon as we connect a load, a current I2 starts flowing through the transformer secondary winding. Now, whenever there is a current, a flux will be produced. Now, due to this current, a flux phi 2 will be produced into the transformer secondary winding. Now, the direction of the flux phi 2 will be try to oppose its causes, and the cause of the phi 2 is the phi. Therefore, the direction of phi 2 will be in opposite direction of phi. Here, the flux phi 2 this is the flux phi 2 is due to current I2. in opposite direction of phi. Opposite phi is, if the phi is clockwise, phi 2 will be the anti-clockwise. Therefore, the net flux through the transformer core, phi net, will be the phi minus phi 2. Opposite direction, therefore minus sign will be there. Since it is opposite, therefore phi net, the resultant flux tends to reduce. As a result, E, induced EMF, also try to reduce, and E2 also try to reduce. In order to make the induced EMF constant, that means E equal to constant, an additional current will be drawn from the supply. The additional current is I2 dash. Now, due to I2 dash, again a flux will be produced into the transformer core. Due to current I2 dash, the flux phi 2 dash will be equal in magnitude of phi 2 but in opposite of phi 2. Phi 2 dash will be minus of phi 2. The direction of phi 2 will be in opposite of phi 2. This is the phi 2 dash due to I2 dash, equal but in opposite direction. Then the phi net equal to phi minus phi 2 plus phi 2 dash. Here these two quantities will cancel out, that is equal to phi equal to constant. Therefore, the working flux phi remains constant. In this reason, the transformer is also called the constant flux device. Transformer is so designed that MMF at primary due to I2 dash will equal to MMF at secondary due to secondary current I2. Now, the MMF is the ampere turns, primary winding turns, number of turns N1, current is I2 dash. Therefore, N1 into I2 dash equal to the number of turns N2, current I2. N2 into I2. From this equation, we can write down N1 by of N2 equal to I2 by I2 dash. This is called the exact current ratio. Now, the primary current I1 is equal to no load current I0 plus I2 dash. Here the no load current is very small. It is approximately 5 to 6% of full load current. Therefore, I can neglect the no load current. Then I1 primary current will be I2 dash. Therefore, from this relation I can write down N1 by N2 is equal to I2 by I1. And this relation is the approximate current ratio. Now already we have derived one relation equal to E1 by E2 equal to N1 by N2. In the EMF equation of transformer video, we have derived this relation. Link will be given in the description box. You can see how the relation has been established. That is, this is the voltage ratio. And this is the turns ratio. Now we have derived another relation N1 by N2 equal to I2 by I1. Therefore, we write down this is the I2 by I1. And this is the current ratio. This is current ratio. If we have to find out exact current ratio, then we have to use this formula. If we have to find out approximate current ratio, then we have to use this formula depending upon your numerical data. Now let us draw the Phasor diagram of transformer. Here phi flux phi is common both primary and secondary winding, therefore phi is taken as a reference. Phi equal to phi m sin of omega t sinusoidal and I mu equal to I m sin of omega t. Therefore, the magnetizing current will be sin omega t, phi equal to sin omega t, same phase. The magnetizing current will be in same phase of phi. Now the E equal to d phi dt. If we derivative of sin omega t d phi dt, then E proportional to cos of omega t. That means E induced EMF E1 and E2 will lags phi by 90 degree. Here, depending upon the N1 by N2, E1 may be greater than E2 or less than E2. E1, this is the E2. According to Lenz's law, the induced EMF is opposite of supply voltage. Therefore, E1 will be minus of V, supply voltage V. It will be the opposite direction of supply voltage will be opposite direction of E1. Now, if the lagging power factor load, then I2 lags E2 by theta 2. Now, another component of no load current is IW, working component. It is in phase of supply voltage. This is the IW. Now, the Phasor sum of IW plus I mu is the I0. This is the Phasor sum of I mu and IW. This gives you no load current I0. Now, depending upon the number of turns N1 and N2, there will be a current here. There will be a current I2 dash. This I2 dash will be opposite of I2. This is the I2 dash. The sum of I0 plus I2 dash, I0 plus I2 dash is the primary current I1. Thus, Phasor sum of this is the primary current I1, and this is the theta 1 transformer primary power factor. Here one point is clear. The no load current I0 is the I mu magnetizing current plus working current IW, and primary current I1 is the sum of I0 no load current plus I2 dash. Here this relation is not the arithmetic relation. Here we do mistake in numericals in exam. What we do generally, suppose this is 2 ampere, it is 1 ampere, 2 plus 1, 3 ampere. Okay, suppose this is 2 ampere, it is 1 ampere, no load current will be the 3 ampere. Here we do mistake. This is not the arithmetic relation, this is the Phasor relation. Bar will be there, and therefore I0 will be root over of I mu square plus IW square. Similarly, I1 will be root over of I0 square plus I2 dash square. Let the primary winding resistance is R1 and reactance is X1. Similarly, the secondary winding resistance is R2 and reactance is X2. Then here I2 into R2 plus J into I2 X2 gives you E2. Similarly here I1 into R1 plus J into I1 R1, here J into I1 R1, J into I1 X1, sorry, J into I1 X1 gives you supply voltage V. Let us practice a numerical. A single phase transformer has a turns ratio 1:2 and is connected to the purely resistive load as shown in the figure. The magnetizing current drawn is 1 ampere. Here I mu is the 1 ampere. The secondary current is 1 ampere. That means I2 is again 1 ampere. If the core losses and leakage reactance are neglected, the primary current is how much? Then you have to find out I of 1 equal to what is it? All of you know, just from this theory I have derived your I1 primary current I1 is the Phasor sum of I2 dash plus I0. This is the Phasor sum. Again the I0 no load current is the Phasor sum of IW plus of I mu. This is again Phasor sum. Here the losses transformer core loss is neglected. Therefore IW is 0. I can say the no load current I0 is the I of mu. Now we have derived one relation that N1 by N2 is equal to I2 by I2 dash. What is N1 here? Here N1 turns ratio 1:2. Therefore this is 1, this is 2. You can write down 1 by 2 and this is I2 is again 1, this is the I2 dash. Therefore I2 dash equal to 2. From here the I0 is a magnetizing current and it is given, magnetizing is given 1 ampere. Therefore I can write down primary current I1 is the, since it is Phasor sum, it will be I2 dash square plus I of mu that square. That is given by root over of 2 square plus I mu equal to the 1 ampere, 1 square, so this 2.24 ampere. Therefore this is the 2.24 ampere is the answer. Friends, thanks for your great support to get EDUCARE. A huge amount of response has been given to my newly launched channel, and the channel is growing very fast. Friends, I need your support for my motivations. If you really like my videos, please subscribe the channel, write down comments if you have any doubts, and like and share to your friends so that I get motivated. Thank you once again.